Well, before we go on to the next theorem, let's make one final comment about the intermediate value theorem and what it implies. Basically, if you have the same hypothesis as the intermediate value theorem, which was 3.16, you take f, a function from a into r, let it be continuous, and a, the domain, being connected, and I'm going to assume that f of a is less than f of b. We could make a similar statement if it were the other way around. If that's true, then the interval from f of a to f of b is completely contained in f of the interval a to b. Not necessarily equal, although we saw an example where they were, if it were a straight line, for example. And we can deduce from that that connectedness is preserved by a continuous function. So very, very informally, I could say f of a connected set is equal to another connected set. Connectedness is preserved by a continuous function. So in a continuous function, f of an interval will give you an interval. Because remember that connected sets all have the form of an interval. Okay, let's take a look. Powerful theorem, stated slightly different. If you've taken complex analysis, you've seen something like this. Theorem 3.17 says, if p is a polynomial of odd degree, remember what the degree is, the largest exponent of the x's, then p has a real zero. And let's just think about what that means. In pre-calculus, we know this is true. We, of course, didn't prove it. But in pre-calculus, we know that an odd degree polynomial either rises left and rises or falls left, or rises right or falls right. So after some ups and downs, perhaps, eventually it's either going to skyrocket up or skyrocket down. So in either case, you're going to have part of that polynomial crossing the x-axis, and that's what we mean by a real zero, a real root. Now let's just take a quick example of a counterexample. In other words, not an odd degree, but an even degree polynomial. Maybe x squared, which graph looks like a parabola. Well, this has a real zero, but if the parabola opens upward and is above the x-axis, it has no zeros whatsoever. But this theorem is saying that if it's odd degree, a polynomial of odd degree is absolutely going to pass through the x-axis at some point. Okay, let's prove that. Here's the beginning of the proof. It says, let p of x be a polynomial. All of the ai's are constants, just real numbers. a0 plus a1x to the 1 plus a2x to the 2, all the way up to an x to the n. We want n to be an odd number, and an is not allowed to be 0, because otherwise it wouldn't be a degree n polynomial. This term would go away. Let's get one of the simple cases out of the way right away. If a0 is equal to 0, that means this term doesn't exist, and all the other terms have an x in them. So p of 0 would give me 0, and we're done. So if a0 is 0, we get a trivial proof. So let's assume that a0 is something different from 0. All right, let's let a new polynomial, q of x, equal what we get if we take p of x and divide every term by x to the n power. So I could say p over x, or p of x over x to the n, which would be what? a0 over x to the n plus, well, when I divide by x to the n, I'm only going to get x to the n minus 1 on the bottom because I have an x on top here. So it would be a1 over x to the, sorry, that's x to the n power. This would be x to the n minus 1 power, plus dot, 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 and we'll go all the way to, maybe I'll go to a n minus 1 over x, plus the last term would be a n. Well, that's perfectly legal to do, except for the fact that I'm not allowed to divide by 0. So let's just make a note on the real numbers, not counting 0. 0 is not in the domain of q of x because we're dividing. X can't be 0. Let's choose an epsilon greater than 0 such that it is smaller than an. The leading coefficient of p of x, but this would be that kind of that constant term in q of x. And for I from 0, 1, all the way up to n minus 1, there exists a ki, just some real number ki greater than 1, such that ai divided by ki is less than epsilon over n. So let's just convince ourselves that that's true. Epsilon is just a tiny number. We think of it as being a small positive number. The AIs are all of the coefficients. There's n of them, or let's see, technically they're n plus 1 because it starts at 0, a0 through an. They're just numbers. So I can choose a k for each one of those AIs that is so big that dividing absolute value of AI by ki gets me a number that is smaller than this is just some fixed number now. We know epsilon, we know n, so just make k really big to make that true. Since there are a finite number of i's, a finite number of k's. Finite numbers have a min and a max. A finite set of numbers every time has a minimum and a maximum. So let's just let k equal the biggest among all of the ki's. So I'll do k0, k1, all the way up to k n minus 1. K is going to be the biggest, or maximal. All right, so if we do that, let k be defined that way, then whenever the real number x in absolute values is bigger than k, we're going to get the following. Absolute value a0 over x to the n plus a1 over x to the n minus 1. Let's go all the way to the end, which would be a n minus 1 over x. Notice in this one, we only have n terms, where we have n plus 1 terms in this one. So we left off the an term in this. It wasn't being divided by x. Well, by the triangle inequality, this is going to be less than the sum of the absolute values. The absolute value of the sum is less than the sum of the absolute values. So a0 over x to the n plus dot, 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 all the way up to a n minus 1 on top in absolute values over that. Okay, that's the triangle inequality if you want to write the justification. And then the next thing is going to be, we're using the fact that k is a smaller number than the absolute values of the x, or absolute value of x is bigger than k. So we can replace the denominators here with k. We're increasing this because we're decreasing the denominator. Running out of room, so I'm going to go a little bit to the right now. Well, what do we know about each one of these terms? We know this. So that's less than, strictly less than, epsilon over n plus all the way up to the last one, which is equal to epsilon. I'm adding up n terms right here. Maybe I'll note that there are n times n of these to get epsilon. All right, let's see. I'm going to continue to the right. Thus, since a n in absolute values is bigger than epsilon, and x is bigger than k in x in absolute values, we see that q of x and a sub n have the same sign. And let's see if we can make sure that that's clear. Here's our definition of qx. If this is really small, and this is really small, and all of these are really small, in other words, these all in absolute values from here to here add up to be less than epsilon. They're very, very tiny. Epsilon is less than an. If that's really tiny, you can make it as tiny as you want. These two have to have the same sign. Q of x and this will have the same sign. Notice we could write this like P of x is equal to Q of x times x of n, x to the n. P of x is equal to Q of x times x to the n power. All right, therefore, if an, not in absolute values this time, if an is a positive number, then x greater than k, greater than or equal to k, I'll say, implies that P of x is greater than 0. And, I'm going to put it all in one line because I'm running out of room, x greater than or equal to k implies P of x is greater than 0. Alternately, x could be less than negative k. And that implies that P of x is less than 0. That's just using the definition of the absolute value. If this is true, it means that x is bigger than k, or negative x is less than negative k. That's just the definition of an absolute value inequality. Otherwise, sorry, I'm writing that small. I want to line it up here. Otherwise, an is less than 0. And that gives us that x is greater than or equal to k, implying the opposite. P of x less than 0, and a being less than or equal to, a in being less than or equal to negative k implies P of x is greater than 0. Essentially, that means in either case, we have found that the value of the polynomial for one value is positive and one value is negative. So we can employ Bolzano's theorem or modified Bolzono's theorem. So in either case, there exists an x1 and an x2 in the real line such that P of x1 is less than 0 and P of x2 is greater than 0. So we're basically done. One more concluding sentence. I'm going to put my therefore over here. Therefore, there exists an x0 in between x1 and x2, or in the interval, open interval from x1 to x2, such that P of x0 is equal to 0, and that's by Theorem 313, Bolzano's theorem. And that's what we're looking for. Oops. Yeah, we're looking for P having a real 0. So we found x0 such that P of x0 is equal to 0. And that concludes the proof.